Hello. So this is the second live Leaving Cert Maths Guide lesson. So last time, well, it was the first thing. It was the first go. So if you heard it, we ended up with some audio interference, and so there were some issues. But that's what happens when you try something for the first time and you move on. So today we're doing probability. And actually looking at the syllabus, it's possible, and in fact that's what we're going to do, to do the entire probability syllabus in one day. So it's only going to take slightly over an hour. And that's what we're going to do. I imagine it probably makes sense to, do it the first time, and you'll hear what the main ideas are, get introduced to the jargon, the new technical terms and stuff, the language which is used when you're dealing with probability. And then, things kind of make sense. And that just kind of makes sense after you've used it many times. So basically, if you go through the lesson, then it should make sense. And then if you try the problems from your book, it should just make sense. It should kind of go, oh, yeah, I know how to do that. We're only going to do the entire ordinary level content today. But as I mentioned last week, today's 16th October. The honors material, or the higher level stuff, will be put up over the weekend, most likely. Because, the higher level is just a little add-on to what you do at ordinary level. So you need to do the ordinary level stuff for a higher level anyway. Then I'll put up some problems, so you can practice on probably Monday. And then the solutions for that, or for those, will be up next week. So something like that. It's not set in stone. And in fact, after you've done that, we will look at past papers. So soon enough, we'll look at, say, a past paper for probability, maybe like a few years ago or last year, I don't know. In fact, if you should be able to do any of them. So then you'll see, oh, you mean I only spent 1 hour and now I can actually do the exam question? Because, unless you see you can do that, then, you're not, why would you believe that you've actually done anything? You'll kind of go, oh, I've only spent an hour. What did we do really? Well, you've actually done everything. You can, in fact, sit the exams. So that's the plan. So we'll start with the lessons. I've broken them into 4 bits. So, it's not like they're actually 4. It's not like you have to sit there for an entire hour. In this live thing, it's going to be going for an hour. But it's going to be on YouTube. So, you can jump ahead, pause, whatever, and view it in whatever way suits you. Though I imagine if you do set 1 hour aside, it kind of flows. If you set yourself, okay, I'm gonna do maths for that hour, then your mind kind of goes, okay, I'm doing maths now. You don't get distracted by other stuff. You have set aside that time to do the maths. And you can be in maths mode for an hour, and then that's done. And remember, you're talking about an hour to do the entire probability content, which you probably have that's worth a couple of months, given that you had 2 years to do the entire syllabus. And this is not a non-trivial part of the syllabus. So, you can easily spend an hour. So on to the lessons. Where is it? So obviously, still some technical problems. Here it is. And I'll just start again. Okay. So this is the first lesson where we set up the basic framework. What do we mean by probability? We define the probability of an event A happening as the number of times event A happens divided by the total number of events. So does that make sense? Well, when we're thinking about probability, I suppose we can think of two examples are pretty handy. So tossing a coin or rolling some dice. So say, for example, I tossed a coin. Now it could be heads or tails. So toss coin, it could be heads or tails. So actually the possible things it could be is called the sample space. So sample space equals set of possible outcomes. Now, so say I tossed a coin and it came up as heads. Well, then this definition would mean, okay, probability of heads is equal to 1. Because I tossed a coin and it came up as heads, and I only did one event. And the probability of getting tails is 0. So this is if I only tossed one coin once. So tossed coin once. So then my possible outcomes, as I said, the sample space was head or tails. So that's pretty useless. I mean, that's telling me that the probability of heads is not equal to the probability of tails, while, that is nearly a given. I know you toss a coin because the probability of heads and tails are equal. So when you're trying to decide, whether to do A or B, you toss a coin and it's supposed to be fair. So go back to the drawing board. There's something wrong there. So this makes no sense. So then we have to kind of change something, because it kind of makes sense, that the frequency of how often A happens compared to, just the frequency of how often A happens, it kind of gets our intuitive sense of what probability is. But it's just that this definition clearly has something wrong. So the tweak or the fix for this is to basically go, well, I didn't mean that. I didn't mean tossing a coin once. What I meant was if you did it many times. So now we have to go probability of a number of events where a number of events is large. So meant many times. So mathematically you could say, and you do, so as number of events goes to infinity, which is kind of a fudge, but it's a more precise thing. I mean, it leads to a probability which is closer to what we wanted to get. So how would that work? Well, of course, you're never actually going to do it a infinite number of times. But say you toss a coin 10 times. Well, then you'd expect, on average, you'll get 5 heads and 5 tails, though you could have only 4 heads and 6 tails, or maybe 3 heads and 7 tails, depending on how it went. And you can do it yourself. Just toss a coin 10 times, and you're not always going to get 5 heads and 5 tails. So that's why you actually, or we stretch the number to infinity, basically going, okay, yes, 10, there's going to be a bit of variation. You're not going to get a probability of being a half, because what we're saying is, on average, you will get, if you toss it 10 times, you'll get 5 heads out of 10. So the probability is 0.5. But there'll be variation. So if you were to toss it infinite number of times, then that number, the probability will get closer and closer to a half, which is more sensible. So what do I want to add to that? So the probability A, or is a number. From 0 to 1. So you can see that follows from our early definition that if the event doesn't happen at all, then the probability will be 0. While if the event happens all the time, then the probability will be 1. So it's like if you were to, so the two standard examples would be, okay, if I roll some dice, a 6-sided dice, so it can be either 1, 2, 3, 4, 5, or 6. Well, then the probability of getting a 7 is going to be 0 because it's never going to occur. If I were to look for the probability that the number is between 1 to 6, well, that's going to be all the time. And if I were to ask what's the probability of getting a 1, well, if I was to do it many times, it should be 1 in 6. So that is the basic framework that we're looking for. That this is the golden formula, or our core definition, really, that the probability of an event happening is we define as the number of times that event happens divided by the number of events. So, and you want this, so we're going to tweak this as number of events goes to infinity. And in a practical sense, that means when the number of events is large. So knowing that it's converging slowly to the actual probability. These are also related to Bernoulli trials. Since tossing a coin is a Bernoulli trial. So if a Bernoulli trial is one where you do the same thing again and again. So do the same thing again and again. Now, the reason this is kind of remembered is because this is one of the early things that, so when people were beginning probability, they didn't have any formulas. They didn't really know what they were trying to do. So Bernoulli investigated what happens if I keep tossing a coin, and just studying, just looking to see whether he could say anything about that. Otherwise, a lot of early probability was related to, I suppose, gambling, card games, dice. One of the things that you're expected to know is, okay, so at most you're looking at I think 3 trials. So even though it's a repeated trial, meaning it could go on forever, as far as we're concerned, we're interested in up to 3. But I mean, you get the main idea, which is what you're looking for. So say I was tossing a coin 3 times. Well, again, look for the sample space. So it could be heads, 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 tails. Could be heads, tails, heads, heads, tails, tails. Then it could be tails, heads, heads, tails, head, tails. So I'm just writing the same thing above me, but using tails for the first toss. So the first result, if I toss a coin once, there can be two possibilities. If I toss it twice, there's four. If it's three, it can be eight. And I've got all eight listed here. So now, if I want the probability of something, I go, okay, I just count how many of these eight are A, I think about what am I trying to find the probability for? So I just in general I'll just call that A, and then I count how many of these eight belong to A. How many of these eight events would I count? Would I include, or would I count as being an A event? That's a bit waffly. So, well, in particular, one of the questions that are on the syllabus is, okay, what is the probability of the first tails being the third coin toss? So, probability of first. Now, it could be tails or heads, but say I'm going to say first tails being the third coin toss. Well, I'll just look through the 8 possibilities. Now, if the first toss is the third coin, or the first tail is the third coin toss, that means the previous ones have to be heads. So the only one that matches the description of what I'm looking for, like the only scenario where I'll get the first tail is the third coin toss, has to be head, head, tail. So that is head, head, tail. So then there's only one of the 8 possible events fulfills this. And with our definition, we just go, well, so the probability, the number of events, number of these that are A is equal to 1, and the number of possible events are 8. So then the probability is equal to 1 over 8. So the probability of the first tail being third toss is equal to 1 over 8. So that's our launch or introduction into probability. We have a basic framework, that we count the number of events of the type we're interested in and divide that by the total number of events. 2, we know that we need to do this many times. So and that we have this idea that technically we mean that this needs to happen infinite times to get to the answer that we're interested in, though practically we'll be getting closer. We want to do the thing many times. So whether that means 100 or even 20, that we're converging to the answer. And then finally, we introduce the terminology, the jargon in this topic. So we've heard about what the sample space is, which is the total number of possible outcomes that we could have. So that's the first lesson and one of the bigger ones. It's the main idea, I mean, what do we mean by probability? So then we're going to be looking at how we count different things. So how we count the number of coin tosses or things. So since there's enough lessons to come, I'll just pop on to the next lesson. So how do I do that? Click here. Okay. So still have some bugs to iron out. Nearly there. This looks good. Okay. Now, the Venn diagram is a useful way at looking at sets. So say I have a classroom where there are 32 people. Then we have two groups within the classroom. So we call the first one A, which is people who like ice cream. And then we have another set, B, which is people who like chocolate. So the way we denote this is A, so that's the collection of people who like ice cream, and B, the people who like chocolate. Now, the usefulness of this, or the power of this, comes in because it provides a vocabulary, a way to be basically more precise. So A is the collection of people who like ice cream, but everybody who likes ice cream doesn't necessarily like chocolate. So this lets us be more precise. So say there's one person, or say there's 26 people who like chocolate and ice cream. So this area, which is both A and B, would then have 26 people. And then this area is within A, but not in B. So there's one person who likes ice cream, but doesn't like chocolate. And there's one person who likes chocolate, but doesn't like ice cream. And then we put in 4 here, because that's the number of people who are not in A or B. Because there's 28 people who like ice cream or like chocolate. We said U is equal to 32. That means the entire collection of people. So in this case, the entire class has 32 people. So there are 4 people who didn't like ice cream or chocolate. And one more thing, we also say A prime to denote the complement of A. So that's the collection of people who are not in A. So if A has 27 people, A prime would have 5 people in this example. Okay, so what does this let us do? Well, the main thing I wanted to talk about was the concept of and. So in normal everyday usage, it's not basically precise enough. So when it comes to probability, when we say A and B, people who like ice cream and chocolate, that means the 26 people. But otherwise, it's vague. If I say people who like ice cream and chocolate, that could also mean the set of people who like ice cream and the people who like chocolate. So that could also have meant 28 people. So when we say and, we mean A intersection B. So those who like both ice cream and chocolate, or those who belong to both A and B. Otherwise, you have or. So that would be A union B. So this sign means intersection. And that means union. So that means like ice cream and chocolate, as well as just ice cream or chocolate. So A union B would be all 28 people, while A intersection B would be 26. So I'll say that's 26 people, while that is 28 people. So that's just a way, or that Venn diagrams provide us with a language to be more precise. So then when we're dealing with other issues later on, we can do it because we're able to distinguish between and or. And finally, there's also the concept of the fundamental principle accounting. So that is so if you can pick A in X different ways, and you can pick B in Y different ways, then you can pick AB, so A followed by B in XY different ways. So if you think of rolling 2 dice, then you can pick the first roll can be done in 6 different ways, and the second one can be done in 6 different ways. So rolling 2 dice can be done in 36 different ways. So that's 2 done. 2 to go. I'll just set up the third one. And here it goes. So we just have a couple of concepts to touch on before we wrap up on probability. So the first one is the expected value. So think of a game. If you toss a coin, and if you get heads, then you win €2. And if you roll, or if you toss tails, you lose. You don't get any money back. And it costs €1 to play. So how's that work? Well, as the rules say, you just toss a coin, and if you get tails, you lose the money. If you get heads, you win €2. The expected value is, well, you multiply the probability. So in this case, heads occurs half the time, by the amount that you'll win if you if you get heads, plus the amount you'll win if you roll or if you toss tails by the probability that you'll get tails. So that would be the expected value from this game. And when you multiply that out, that works out at 1. So it costs you 1, and on average, you'll win back 1. In other cases, it could be, say, you roll some dice, and if you get the numbers 1 or 2, so 1 or 2, then you'll win €1. If you get 3 or 4, get, say, 50 cents. And if you roll 5 or 6, nothing. Well, then we do a similar process, work out the expected value. So expected value is equal to, well, you have a 1 in 3 chance of winning €1. So 1/3 multiplied by 1 plus, well, a 1/3 chance of winning 50 cents and a 1 in 3 chance of winning nothing. So when we add this up, we get, well, 0.33 plus 0.167. So 0.497, roughly. So if you were to pay €1 to play this game, well, you could win €1, but on average, in the long run, you tend to lose money. So this is actually related to the other concept that we wanted to look at, which is fair value or fair game. So basically, a fair game is one where the expected value is that you get your money back. So in the first game, where you toss a coin and you'd get €2 if you, or, well, you'd win €1 if you win. But anyway, so you'd get €2 if you win and nothing if you lose. So half the time you'd lose €1 and half the time you'd win €1. So it's a fair game. While in the second game, well, with the dice, in general, you'd be losing money. So why would you play that? So a fair game is you get your money back. The expected value is equal to the cost. Somewhat related to that. So one way that a game could be unfair is that it's not actually 50-50. It could be that, you're told the game you're playing is you win €2 if it's heads and you lose if it's tails. But actually, you get tails 70% of the time and heads only 30%. So then you wouldn't actually get your money back. Actually working that out. So say unfair coin used. So 30% chance of heads. Well, then the expected value would be a third times 2 multiplied by, 0.7 times 0. So then the expected returns from the game are, or is, 60 cents. So then it wouldn't be fair, even though when the game was described to you, it's supposed to be fair. The other variation is bookies. So what a bookie would do is allow you to choose. You can bet on heads or tails. But what they'll do is they'll say, if you win, I'll give you when you're 80. So here, if a win, you get €1.80, and if you lose all your money. So in that game, well, we can work out the expected value. You have a 50% chance of winning, but you'll only win €1.80. So then that means the expected value is going to be 90 cents. So then that way, the bookie tends to win and the bettor tends to lose. Finally, expected values are also used when you're trying to make a decision. So it can be used for decisions. So you think of various scenarios, you work out what the expected values are for each of them, and you pick the one which has the highest expected value. Just looking at that again, I once wanted to add that, I said that a fair game is, where you get your money back, but that's on average. So not obviously every time. So if I think about the coin tossing example, where if you win, you get €2 back again, but if you lose, you lose. Well, I mean, if you play that game once, you could say, oh, it's going to be heads, you toss the coin, and it's tails. So then, of course, you lose. And so then, in that case, you don't get your money back. It's more if you did it many, many times, that on average, you get your money back, as opposed to always. So now we only have one lesson left. And this is a pretty long one, but we've actually gone through the entire probability strand in slightly more than an hour. So set that up. And here it goes. So I'll just click, click, click. Imagine you had a bag. So you have a bag. with 5 balls. Numbered 1 to 5. So kind of like, the Lotto or Euromillion. So how many ways can I pick them? Question. How many ways can I pick them? Now this is different from what we've done so far. So this is different from tossing a coin or rolling some dice. And the reason for that is that it changes. So with the coin, we just kept tossing a coin. So when we tossed the third coin, it was the same answer as tossing the first one. You're going to get either a head or a tails. In this case, we begin by having 5 balls in a bag. We randomly, we put our hand in and we can't see what we're pulling out, and we pick out a number. But then when we pick the second ball, we don't put the ball back. So this type of setup is known as without replacement. So in a way, the coin toss would be if you had 2 balls, one with H on it for heads and one with T on it for tails. And then you just put your hand in, you pulled out a ball, you went heads, and now you put that ball back in again, randomized it, so you didn't know, you forgot what, you didn't know which ball is which, and then you pulled another ball out. That scenario is known as with replacement. So you can keep doing that. So likewise, you could have 6 balls numbered 1 to 6 and randomly pick a ball out and then replace it. And then that would be the same as rolling some dice, because you'd be picking a number from 1 to 6 and every time would be the same. But in the without replacement scenario, initially, if I pick 1 ball, there are 5 possible outcomes. It could be 1, 2, 3, 4, or 5. But now when I'm picking the second ball, there are 4 possibilities, because there are only 4 balls left. Now when I pick the next one, there are only 3 left. Then there are only 2 left. And finally, there's only 1. So if we're picking 5 balls, the possible combinations are 5 times 4 times 3 times 2 times 1. So what's that? That's 5 times 4 is 20. 3 times 2 is 6. So there are 120 possible results. Now, 2 things to say here. So this one can be any one of 5, 4, 3, 2, 1. Whether the numbers came out as 1, 2, 3, 4, 5 or 4, it doesn't matter. All I care is which numbers came out. So if I work it out like this, there are 120 possibilities. But if the order doesn't matter, it's not the same. So if I was to ask you, what are the possible numbers that I could pick? So here, the order matters. If it didn't, and I only cared which numbers came out, so which numbers were picked, then, well, there's only one answer we can get. So if I only cared which numbers were picked, then there's only one outcome. Because if I pick 5 balls and they're numbered 1 to 5, in the end, I know I'm going to pick all 5 balls. So, yeah, so there's only one outcome, since if picking five balls from 5, then picking all of them. So this process, this procedure of 5 times 4 times 3 times 2 times 1, that tells us how many ways we can arrange 5 things. So I could pick the 5th thing first, the 4th thing second, or there are 5 possible numbers that I could have as my first number. But if I've used up one of them, if I've already picked which number is going to be my first number, well, then there's only 4 possible ones that can be the second, and so on. So that in that way, I got 120 possibilities. But if I don't care which order they're in, if I only care which numbers I picked, well, in this case, there can only be one possible result, because I know I'd be picking all 5. Now, if, on the other hand, I was to pick 5 numbers from 6 balls, well, then it would be different. So we'll just look at that next. So say I had 6, or to make it simpler, say I had I picked 2 balls from 3. So say I had 3 balls, so numbered 1 to 3, and I picked 2. Well, the first ball can be any one of 3, and the second can be any one of 2. So then there are 6 possibilities. Now, that's if I care which order they're in. So, if the order matters. So let's think about it. Say I had 1, 2, 3, 1, 2, and 3. Well, what are the 6 possibilities? Well, I could have 1, 2. I could have 1, 3. I could have 2, 1. I could have 2, 3. I could have 3, 1, and I could have 3, 2. So they're the possibilities if I'm picking 2 balls which are numbered like 1, 2, and 3. But if I don't care which order they're in, well then 1, 2 and 2, 1 are the same to me. So again, if I think of Euromillion, all I care about is if my numbers come up. I don't need to get them in the exact order that they're drawn. So in this case, so if don't care about order, then divide by 2. Since I'm picking 2 balls, and I could have, if the order doesn't matter, then 1-2 is the same as 2-1, and 1-3 is the same as 3-1, and 2-3 is the same as 3-2. So where does that leave me? Well, I know I can arrange n balls in n multiplied by n minus 1 multiplied by n minus 2 and so on till I get 1. If order doesn't matter, or if order does matter, sorry. If order matters. And this is done so frequently that we actually have a term for it. This is called n factorial, and denoted, or written as, n with an exclamation mark. So n factorial means n multiplied by n minus 1 multiplied by n minus 2. In particular, so 3 factorial is equal to 3 times 2 times 1. Now, what about if the order matters? Or what about if the order doesn't matter? So 3 factorial, n factorial, tells us the number of ways that we can pick n things when the order matters. If the order doesn't matter, well, we divide by n factorial. So if I'm picking 3 balls from 5 things, well, the first step would be to see, well, if I'm picking 3 balls from 5, it can be 5 times 4 times 3. Because the first ball can be any one of 5, the second can be any one of 4, and the final one any one of 3. So that tells us there are 60 ways that I can pick the balls where the order matters. But if I'm picking 3 balls, I would divide by 3 factorial to remove the order dependence. So if order doesn't matter, I'm overcounting. When I do 5 times 4 times 3, it's like, this example. I'll end up having 1, 2, and 2, 1. So I'll have, since I'm picking 3 balls here, I'll have 1, 2, 3, 2, 1, 3, 3, 2, 1, all of which are actually the same 3 numbers. So if I only care about which numbers am I going to pick, then I need to divide by 3 factorial, because that'll remove the overcounting. So then this tells us how many combinations where order does not matter there are. So I'll just do some examples because it can be confusing. So say I'm picking 2 balls from 3. Well, then the first step is how many can I pick where the order does matter. So the first ball can be any one of 3 and the second can be any one of 2. So how many combinations or permutations where order matters. And then since this will lead to 1, 2 being different to 2, 1, since, as I said, the order matters. If the order doesn't matter, well, I'm picking 2 balls, so I'll divide by 2 factorial, which is equal to 2. So that what that's saying, well, it's going to be 6 divided by 2, 3 combinations. So just list them. Well, as we did before, 1, 2 can't have 1, 1 because there are only 3 balls, and I could have 1, 3. I could have 2, 1. I could have 2, 3. I could have 3, 1. I could have 3, 2. So there are the 6 possibilities. But these are the 6 possibilities if the order matters. If the order doesn't matter, well then I can have 1, 2, 1, 3. Well, 2, 1 is the same as 1, 2 because the order doesn't matter. I can have 2, 3. 3, 1 is the same as 1, 3, so that's not different. And 3, 2 is the same as 2, 3. So only 3 possibilities if the order does not matter. So just writing this in general, if I'm picking R things from N, so if picking R things from N, so, N will be bigger than R, then the answer is going to be N multiplied by N minus 1 multiplied by ... N minus R plus 1. Because when I picked 2 things from 3, I had 3 and I ended up with 2. So if I had N minus R, I would have gone all the way to 3 times 1. But I didn't. So you keep going till N minus R plus 1. So that's the top. And then I divide that by R factorial. So when N was 3, I had 3 times 2. N minus R, 3 minus 2 is 1 plus 1. So I stop at 2 on the using this general case. So I would end up with 3 times 2 and stop there. And then I divide by 2 factorial, which is what we did. So this is also commonly done, and this is called, well, it's written as N choose R, and as I said, called N choose R. So they're the main building blocks, and we need these because, well, when we're doing probability, we talk about, we count the number of events of type A and then divide that by the number of the total number of possible events. So what we need to do is to be able to count various things. And when we're doing permutations and combinations, or when we're doing combinatorics, we frequently then result in, or we frequently end up using factorial because it's a powerful way to count the kind of things that we want to count. And then when we want to go that bit further, we end up with using n choose r. And we'll use that next to work out what the odds are for the Euromillion, because that's all we really need. So we'll do that next. So we need one extra piece actually. So that is, if we have two independent events, then the probability of A and B is equal to the probability of A multiplied by the probability of B. So in the case of the Euromillion, there are two bits. First of all, you pick numbers, pick 5 numbers from 1 to 50, and then you pick 2 lucky stars. From 1 to 11. So this is exactly n choose r. So there are 2 bits, 1 and 2. These are, so it's probably, there we get A and B because they're independent, so they're not going to intersect. So that's actually, so the probability, so in this case it would be the probability that you get both all 5 matching the main jackpot, like picking all 5 numbers from 1 to 50 and picking the 2 lucky stars. That's actually just going to be the product of the probability of each. So the probability of A, which is the pick 5 part, is going to be, I want to pick 5 from 50. So 50 choose 5. And then I want probability of B, which is I want to pick 11 choose 2. That's the picking 2 from the 11 possible balls. So now, if you just actually go into Google, you can actually type in 50 choose 5 times 11 choose 2. And there you are. It says 1 is to 116,531,800. And if you go to the Euromillion website, that is the correct odds. So that's pretty much it. So when you're doing without replacement, you know, the number of things that you could get changes. So every ball you pick out, you began maybe with 5, but the next ball there's only 4. So you want to keep tab of that. So then that leads to using factorials. So there were basically three scenarios. One was if you're just looking at how many ways can I arrange 5 balls, where the order does matter, that goes to that leads to the introduction of factorials. And the second one is if I was to say pick 3 balls from 5, well then I just do 5 times 4 times 3. So I don't do a full factorial. So say you have a bag and it has 4 red balls and 2 black. So the question is, you pick 3 balls, what is the probability that you get 3 red? That get 3 red. Well, in a tree diagram you start at the beginning. Now I could pick a red ball or I could pick a black ball. I can write the probability there. The probability of picking a red ball is 4 out of 6. Because there are 6 balls and there are 4 red. So the number of reds are 4 divided by the total number, which is 6. I could pick a black ball. So the probability is 2 over 6. Since there are 2 black balls and there are 6 total balls. So then what? Well, when I pick the second ball, I could end up with red, 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 black. Now I could write this as red. I mean, I've already got red here, so I could write red and black. But I'm just choosing to write it as red, red, since at this stage I have 2 balls. Well, if I've already picked a red, then there are only 3 red balls left out of 5. So I would say the probability of picking a second red is 3 over 5. The probability of picking a black, well, there's 2 out of 5, because there are 2 black balls and there are 5 at this stage. Likewise here, if I picked a black ball already, well, now there are 4 red and 1 black left, so the probability is 4 over 5 of picking a... I've got red, 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 black. So if I picked a black, and the probability of picking a red is going to be 4 over 5. The probability of picking the second black, well, there's only 1 black left at this stage, so the probability is going to be 1 over 5. At this stage, the probability, if I pick 2 reds already, well, there's only 2 reds left and 4 balls. So I'll need the 2 reds out of 4, so the probability of getting red, red, red is 2 over 4. If I picked a red and a black, well, then there are 4 balls. So I could pick another black, or I could pick a red. So I've already picked a red and a black, then that means I've got 3 and 1 left. To pick another, there's only 1 black ball left, and out of 4. So there's a 1 in 4 chance. Here as well, there are 2 reds. Wait, if I picked, using conservation here, if I picked a red and a black, then there are 4 balls left. There are 3 reds and 1 black. So there are 3 possibilities here. So 3 over 4 to end up picking a red when I've already picked a red and a black. If I picked a black and a red, so we can basically go through all the possibilities here. But my question was, what is the probability that I get 3 reds? Well, I can't get 3 reds using any of these, So actually, I only need to know this. So in order to pick 3 reds, I would first, so to get 3 reds, I would have to first of all pick 1 red. So the odds are, 4 out of 6. Next, I would only have 5 balls left, and I would need to pick 1 of the 3 red balls out of those 5, and then there'd only be 2 red balls left, so I would need to pick 2 out of 4. So now in the end, I didn't need to fill out the whole tree to get this, but in various circumstances, you need to in various circumstances, it comes in handy. And you can just kind of see what's going on. To pick 3 reds, I end up needing to, I'll just multiply this out. 3 times 2 is 6, times 4 is 24. And that is 4 times 5 is 20, so that's 120. I'm sure that can be simplified. Well, actually, I can do it here. 3 times 2 is 6. And I have a 6 there. So that has to equal 4 over 20, which is 1 over 5. And basically, the important thing there is that this is without replacement. So, if it was with replacement, then every time we picked a ball, we'd go, oh, red, and then we put it back in again. And then the odds wouldn't change. But since it's without replacement, every time we take a ball out, the odds change. And one of the ways that we can do that is using tree diagrams. So this kind of thing, where you just go, I'm starting here and I pick a red or a black, and then write down what the odds are for each, and that way we can kind of keep tab of how many balls are left. So when I'm picking a ball here, it's different to when I'm picking a ball at the start. So this is called a tree diagram. And they're the most kind of difficult questions that you can come across. And that's the end of the 4th lesson. Actually, looking at it, I don't think I mentioned or. So I talked about if A and B are independent, then the probability of A and B is equal to the product of the probability of A times the probability of B. But what I didn't mention was if A and B are independent, that the probability of A or B is equal to the probability of A plus the probability of B. And you can see that, or you can do that in your head. So if you roll some die, then it could be 1, 2, 3, 4, 5, or 6, or if you roll a dice. So if instead I ask, what's the probability of rolling a 1 or a 2? Well, then you add the probability of rolling a 1 to the probability of adding a 2. And if you go into, into more detail, we can go, well, the probability of 1 is 1 over 6. The probability of rolling a 2 is 1 over 6. The probability of rolling a 1 or a 2, well, there are two ways that you can get 1 or 2, since you can roll a 1 or a 2. So then the probability of 1 or 2 is 2 over 6, which is 1 over 3. So you can see that from that example, but it also makes sense. Otherwise, I'd say if you play this whole video again, it should then kind of be it should be more obvious, since you've already gone through it. Then you kind of, as it's playing, you kind of go, well, yeah, okay, that makes sense. That's obvious. What you can do is write your own notes. You can write you can write the same material in a way that makes more sense for you, because different people, each person organizes thinks differently. So you can basically go, well, that's a messy way of saying that. You could get that point across by saying this. So you can clean it up into your language. Then basically do the problems in your book. So whichever book you have, it'll have a similar set of problems. You'll have some, I would say, type A, B, and C problems. The really simple problems. Then the slightly trickier ones, the ones where you have to kind of use the material that was explained, while the easy ones are, you nearly just write it down. I mean, it's autopilot stuff, but it gets you going and just sees whether you've actually read anything before you're trying the problems. And then you have the problems which are, if you're trying to get an A or a B, the trickier problems where you're going to have to think a bit. So that's the way that you can, well, that'll help you actually remember stuff, because if you think about it and you spend more time on something, you're giving yourself a chance to remember it, to memorize it, to internalize it. And also, once you've done the problems, you can build up confidence, and you kind of go, well, actually, I can do these problems. I was able to do them. So that's pretty much it. If you write your own notes, do the problems with practice, then what more is there to do? And if you're stuck on stuff, well, there's the Facebook page. So, the LeavingCertMathsGuide Facebook page. Basically, if two heads are better than one, we literally have thousands of heads there. So there's loads of people there, and we can just answer the questions. It's all been done before. In fact, if there are questions there, you can jump in as well, because in fact, you should know how to do them. So that's pretty much it for today. We'll be back again next week, and good luck.